grade 11s and grade 12s. In today's video, we're going to be carrying on looking at electricity, electric circuits, and in this video, we're going to be looking at power, electrical power. We're going to be looking at definitions, formulae, important theory, all of that stuff. You want to watch till the end because I give teacher tips along the way. Subscribe for more videos like this. Let's jump right in. Looking at electrical power requires us to start with a simple electric circuit. So let's take a look at the circuit and see what's happening here. We have an energy source like a battery, and what this energy source does, in this case the battery, is it transfers energy into a circuit. So batteries have what we call chemical potential energy, and they transfer this chemical potential energy into electrical energy in the circuit. And then it says here a load, which is something like a resistor or a light bulb or an appliance or something that is connected to the circuit, transfers energy out of the circuit. So we basically have a circuit being this means of transferring energy into and out of. And what power does is power tells us how quickly the energy transfer takes place. So we know that energy is transferred. Does it take place quickly? Does it take place a little bit slower? That is what power is. So if you look at your appliances, you'll have a power rating on your appliances that tells us how quickly the energy transfer is taking place for that particular appliance. So it says a change of a quantity. In this case, it's the change of energy or work per unit time, per second. That is called rate. And I've mentioned this before in my videos. So if you've been watching my videos, you will know that I have spoken about the fact that if you have dividing by time, so if you're talking about per second or per unit time, that is the rate. So power is the rate at which work is done or energy is transferred. So we can write the formula like this. Power is equal to the rate. Rate means divided by time, the rate at which work is done or energy is transferred. So this is the basic formula for power. Power is equal to the work or energy or the rate at which work or energy is transferred. Now, I have mentioned as well in a previous video that work and energy are interchangeable, okay? They're both measured in joules. So if I say work is done, that's the same thing as saying energy is transferred. The amount of energy that is transferred is equal to the amount of work that is done. The unit for power is watt, can be represented by a big W, okay? Watt, that is the unit for power, okay? So if someone says, what is the unit for power? Watt is the unit for power. However, we can also take the unit to be as follows. Remember, power is equal to the change in energy or change in work divided by the change in time, the rate at which work is done or energy is transferred. Energy or work is measured in joules, J, and time is measured in seconds. So what we have is joules divided by seconds or joules per second. We can write that like this as well. Joules per second. Okay, remember per just means divide. Joules per second. So in multiple choice questions, they often try and trick you and they will try and say like, what is the equivalent unit for watt? The equivalent unit for watt is joules per second. They're both the unit for power. There is another very important formula for power, and that is the one on the screen behind me. So power, remember measured in watts, is equal to I, which is current, measured in amperes, A, multiplied by the potential difference or voltage. So if we're working out the power of a particular component like a light bulb or a load or a resistor in a circuit, we can take the current that flows through it and multiply that by the potential difference across that particular resistor. Then we get the power. It is also very, very important to take note of the following, that brightness and power are linked. Power and brightness. So it says we can conduct an experiment that shows that bulbs are the brightest, they shine the brightest when their product of V times I is the greatest. And remember, product means multiplication. If you multiply V, voltage or potential difference, with current, you get power. Okay, so the higher the power, the more power, the brighter, for example, a light bulb would be. And we can prove that with the following circuits. Let's compare two identical bulbs. So each bulb has a resistance of 3 ohms. You can see here 3 ohms and 3 ohms. However, in circuit 1, they're connected in series And in circuit 2, they're connected in parallel. Also take note that the battery is 3 volts in both cases. So basically almost identical circuits, except obviously the connection of the resistors are different. And what I want to show you in this situation is the working out the power of each bulb and see how it differs depending on how we connect them. So remember, to work out power, I'm going to use V times I in this case. So the voltage across the bulb, so it'll be the voltage across this bulb over here, multiplied by the current that goes through that bulb. Now, how are we going to do that? Well, to get the current, remember, current is equal to voltage divided by resistance. This is Ohm's law, and I want to work out the total current of the circuit because the total current will flow through these two bulbs over here. If I take the total voltage of the circuit, it's 3 volts, and I divide it by the total resistance, it's 3 plus 3, which is 6. So the total current of the circuit is 0.5 ampere. That is the current that flows through bulb 1 over here and the current that flows through bulb 2 over here. That's cool. Now I have current. But how do I work out the voltage across this bulb? Because remember, what I'm doing is I'm trying to work out the power of one of these bulbs. I'm trying to work out the power of one of these bulbs. So I need the current that goes through the bulb, which I have. That's now 0.5. And I need the voltage or the potential difference across that bulb. Using the total voltage will not help me because then I will not be getting the power for the light bulb. So how do I get the voltage or the potential difference across this bulb? V equals I times R. The current that flows through this bulb is 0.5 amperes, and the resistance of this bulb is 3. So 0.5 times 3. And that gets me 1.50 volts, which makes sense because I hope you know your circuits. If the total voltage across the battery is 3 volts, these resistors here are in series. They split the total voltage, and they split it evenly in this case because each of the resistors have the same resistance. So if the total voltage is 3 volts, this bulb gets 1.5 volts and this bulb gets 1.5 volts because 1.5 plus 1.5 gives me 3. Okay, cool. So now we know the voltage and we can work out the power of one of the light bulbs. So it'll be 1.5 times 0.5 and we get 0.75 watts. Okay, now let's compare it to the situation where the bulbs are connected in parallel. Still, to work out the power of one of these bulbs, we use V times I. Now, back to our knowledge that we learned in grade 10 about circuits. Because these bulbs are connected in parallel, the voltage across them is the same. And because there are no other bulbs connected in series in this circuit, the battery has a voltage of 3 volts, which means that the parallel connection will have a voltage of 3 volts. That means that this bulb will have a voltage of 3 volts, and so will this bulb have a voltage of 3 volts, because voltage is the same for resistors connected in parallel. What that means is I already know the voltage of this bulb, 3. However, how do I work out the current? Remember, in a parallel circuit, current splits. So the total current will flow through this branch, through the main branch of the circuit, and when it gets to a split here, some of the current will go through the top branch and the rest of the current will go through the bottom branch. So in order to work out how much current is going through one of these branches, I first need to work out the total current. And how do I work out the total current? I use the total voltage divided by the total resistance. I know the total voltage, it's 3 volts. But how do I work out total resistance? I need to use 1 over Rp. Why am I using that? Because they're connected in parallel. So 1 over R1 plus 1 over R2, it's 1 over 3 plus 1 over 3, which is 2 over 3. And then as you know, 1 over Rp is equal to 2 over 3. But I don't want 1 over Rp, I want Rp. So you take the reciprocal, you flip this fraction, so you need to flip this fraction, 3 over 2, which is the same thing as 1.5 ohms. Okay, we now have total resistance. So I need to work out total current by going the total voltage divided by the total resistance. And 3 divided by 1.5 is 2 amperes. Now remember, grade 11s, grade 12s, what this means is that in the yellow portion of the circuit, there's 2 amperes of current flowing. That's the total current. However, so let's take it back to what we're actually trying to work out. We're trying to work out the power of one of these light bulbs that's connected in parallel. So I don't care about the total current. The total current is the yellow. I don't care about the total current. I need the split current because the current splits when it reaches this part of the circuit over here. Some of the current goes through the blue, some of the current goes through the purple. So I'm working out the power of B1. I need to know the current that goes through B1. And because the purple branch and the blue branch have the same resistance, it means that the current will be split evenly. So if 2 amperes is the total current, the top branch will get 1 ampere, the bottom branch will get 1 ampere. Even split in current because the resistors are equal. So that means that the current over here through the blue branch is 1 ampere. And 3 times 1 is 3 watts. So here's a summary of what I just did, breaking down everything step by step and including little notes if you need it. And the main point that I want to show you is the power in each bulb differs a lot. And it's all dependent on how we connected them. Because remember, we started off with identical batteries, 3 volts and 3 volts. And we have the exact same bulbs, 3 ohms in circuit 1, 3 ohms in circuit 2. But just because of how they are connected, it changes the power in each bulb. Because remember, the power is equal to the product of the potential difference and the current. And if you look at when we connect them in parallel, the voltage across each bulb is a lot higher than when we connect them in series. And the current through each branch and through each bulb is a lot higher than when we connect it in series. So we end up getting a higher power, which will correspond to brighter bulbs. And we can see that in this photo over here. When we connect them in parallel, look at how bright the bulbs are. When we connect the same bulbs in series, look how dim the bulbs are. So here we can see we connected it in series because all the current will flow through here. I know they're placed looking like they're in parallel, but they're not. So they're in series. You can see how they're connected here. Here, however, they are connected in parallel. You can see like there's splits in the circuit. There's a branch, and there's a branch. Here's another photo showing the exact same thing. The parallel connected resistors or light bulbs shine a lot brighter than the ones connected in series, and it's all because of the power. So as you can see on the screen, this one over here, that was the first power formula I spoke about. Power is equal to the rate of, or the rate at which work is done or energy is transferred. So work or energy, W, divided by time. Then we've got power being equal to the product of the potential difference and the current. And then we have these two formulae over here. Now, these formulae over here are derived from the ones above. In an exam, we give you all the formulae. So we give you this formula sheet. So you don't need to know how to take 3 equations or 2 equations and put them together to give you a new equation. But it is interesting and it does help you understand science a little bit better. So remember we said power is equal to the product of the potential difference V times the current I. We also know that this is a formula that exists. We learned about that in grade 10 already. Potential difference is equal to the energy per unit charge. So instead of V, I'm going to put this fraction over here. Okay? Instead of voltage here. Voltage is equal to W divided by Q. So voltage is equal to W divided by Q. I hope you can see what I did there. I basically just, instead of saying V, I said W divided by Q because that is my formula that I'm working with. And we also know that current is equal to charge divided by time. Okay? So instead of current, I'm going to put charge per unit time and take a look at what happens here. You can cross cancel those. So what we have is P is equal to W divided by change in time. And that is the other formula, the first formula that I showed you in this video. So this is where we get this formula from. And now once again, back to that P equals V times I formula. We also know that V is equal to I times R. That is Ohm's law that we've already learned about. If you haven't seen those videos yet, check out the links in the description box below. So I can say P is equal to, instead of V, I'm going to say I times R, because V is equal to I times R. So I'm going to say I times R. So I'm saying all of that instead of saying V. And then I'm going to say times I because of that part of the formula over there. And now look, I have I times I. And what is I times I? I squared times R. And if you look at your formula sheet, you get a formula that says P equals I squared times R. And now to derive or get the last formula, again, starting with P is equal to V times I. Now remember, this is Ohm's law. We just spoke about this formula. V is equal to I times R. If I rearrange it, if I isolate the I, so you get I by itself, it's V divided by R. Okay, so I is equal to V divided by R. Instead of writing I in this formula, I'm going to keep the V there, but instead of writing I, I'm going to write V divided by R because they're the same thing. Look at what happens here. So I've got V over 1, because anything that's standing alone can be written over the number 1, times V over R. What is top times top? What's V times V? V squared. What is 1 times R? Just R. And that is how we get our last formula here, that you will get on the formula sheet. So it's pretty cool, but I just showed you how we derive all the formula. Again, you don't need to know how to derive them. I just think it's interesting and it's good to understand it, but we give this to you on your formula sheet. So what I want you to take away from this is that the power of a component in a circuit, so if I want you to work out the power of a light bulb or the power of a resistor, it depends on the 3 following things: voltage, current, and the resistor of a component. You can see that. If I increase the voltage, in this case, I'm going to increase the power. If I increase the currents, in this case, I'm going to increase the power. And I showed you that a little bit early on in the video. So power is dependent on these 3 variables. Now, if you ask to work out the total power in a circuit, it says here, the power of a circuit equals the sum, so adding up, of the power of each resistor. And it doesn't matter if they're connected in series or parallel. So if you look at the circuit on the left side over there, we've got a 20 watt bulb and a 10 watt bulb. Okay, they're connected in series, but again, series versus parallel doesn't matter. 20 plus 10 is 30. Total power is 30. And if you take a look at the parallel circuit over here, we've got a bulb, B1, 5 watts, B2, 10 watts. It doesn't matter that they're connected in parallel this time. Total power is 10 plus 5. It's that easy. A big part of understanding electricity and doing well in this section is understanding the relationship between the variables. So your questions will often ask you, if I change the resistance, or if I look at 2 resistors, one is a higher resistance and one is a lower resistance, they're connected in series, which one will have a greater power or power transfer? You need to be able to use the formulae and the relationships and be able to explain using that. So for example, power in series resistors, if you look at this, it says we're going to use this formula, P equals I squared times R. It says here for B1 and B2, because they're connected in series, the current is the same. You need to know that. Current is the same for resistors in series. So this is the same, which means that this is constant. Okay, same, constant, doesn't change. However, if this one has a bigger resistance, so say that this is 3 ohms versus 6 ohms, because the current is the same for both of them, the one with the bigger resistance will have the bigger power. So resistance is directly proportional to power, or power is directly proportional to resistance for series circuits because current is the same. And if we look at parallel resistors, we're going to use this formula. Think of parallel means like one on top of the other like that, like 2 branches. So we're going to use the formula where V squared is on top of R. That's how I remember it. It's a good way to explain using this formula. Now, when resistors or light bulbs or whatever are connected in parallel, their voltage is the same. Again, that is something that you need to know about circuits. B1 and B2 will have the same voltage. If this is the same, the bigger the resistance, the smaller the power. It's inversely proportional. And you can play around with the numbers and think about it mathematically. It makes sense. If you make the bottom of a fraction bigger, so if I go 1 over 4, 1 over 6, 1 over 8, I'm making the bottoms of the fractions bigger. Or let's start with a half. The bottoms of the fraction are getting bigger, but overall, the fraction is getting smaller. So if you eat a half of a pizza, that's more than eating an eighth of the pizza. So the bottom of the fraction is getting bigger, so resistance is getting bigger, but power is getting smaller because voltage is the same. You need to understand that, and I will be going over past paper questions relating to this. So if you want to see that, check out the links down below. And I'll see you in another video very soon. Bye, everyone.